Happy learning! Today we're going to do an introduction to graph models. Okay, so let's start by defining what a graph is. So a graph, G, consists of two sets. First, it has a vertex set, which we're going to denote by the letter V for vertex. So V of G is the vertex set. And it has an edge set. Vertices are going to be little dots, and edges are going to be lines that connect the dots. Okay, so this is not the type of graph like you would have seen back in high school where you were graphing parabolas. This is a totally different type of object. Okay, what is an edge? An edge is an unordered pair of vertices. Okay, this is very abstract. Let me give you an example, and you'll see this is really not too confusing. All right, so for example, e.g., if our graph is the following, so this is E, A, B, C, D. These are our vertices, and maybe there's some edges. So here's an edge. That's an edge. Here's an edge. And ta-da. All right, so if this is our graph, right, we have a set of vertices, and there's some edges connecting some of the vertices. In this case, our vertex set is just A through E. It's just the set of points. So our vertex set basically represents these labels of our vertices. And our edge set is we list two of the vertices for each of these little line segments. So AB, this is the edge BB. Okay, it's not just B. We need a pair of them to be an edge. So it starts and ends at B, so we write BB for that edge. BC. CD twice, so we'll list it twice. And then finally, DA. All right, so if we know the vertex set and the edge set, we could actually reconstruct our graph. So we don't even need the drawing if we know these two bits of information. Okay, so one thing to note, the drawing of the graph really doesn't tell us, basically the drawing of the graph is not unique. We could draw the same graph thousands of different ways. Okay, so note that the drawing of a graph can take on many different forms. While representing the same graph. Okay, so the way we drew this is not unique. For instance, we could have taken this vertex E and drawn it over here. And it would still be the same graph G. Okay, so for example, if I have the following graph, with 5 vertices. 5. All right, so this graph here is actually the same thing as this graph. Right? How do we know this? It has the same vertex set, so V equals A through E. And we could check it actually has the same exact edge set. AB, BB, BC, CD twice, and finally DA. Or we could write AD, it doesn't matter. All right, so there's many different ways to draw the same graph. And so it's often useful to take our drawing and then represent it as what are the vertices, what are the edges. All right, a little bit more vocabulary. This is going to be a pretty vocabulary heavy video today. If 2 vertices are incident to the same edge, okay, what does it mean? Basically, if 2 vertices are the endpoints of the same edge, we say that these vertices are adjacent or neighbors. Okay, and we're going to be interested in the set of neighbors of a specific vertex. All right, so the set of neighbors of vertex, let's say x, is written n of x. Okay, so capital N means set of neighbors. All right, so if you see this capital N, it's just saying the set of neighbors of a certain vertex. So for example, the neighbors of A in our graph that we've been looking at, what vertices are neighbors with A? Well, that's B and also D. And then just a second example, the neighbors of B are A, C, and B is also its own neighbor. All right, so it is possible for a vertex to be its own neighbor, and that's if there's a loop, right? In this case, we have a loop. And so B is its own neighbor. We call a graph simple if it has no loops and no multi-edges. So this is especially not simple. Okay, so most graphs that we're going to look at throughout this course are going to be simple graphs. There's going to be no loops and there's going to be no multi-edges. And so here, this graph is certainly not simple, right? It has a loop, it has a multi-edge. And then one last definition for today. The degree what is the degree of a vertex? So the degree of a vertex V which we're going to write degree of V. So this means the degree of the vertex is the number of edges incident to our vertex. With one exception, loops. So if we're in the case where we're not a simple graph and we have loops, loops are going to be counted twice. Okay, and we're going to be interested in basically the parity of these vertices. Like what is the degree, and is the degree even or odd? Okay, so we call, so if the degree is even, we call the vertex even. All right, so if a vertex has an even number of edges incident to it, we're going to call it even. And then similarly, if odd. All right, so let me draw that graph again. I shouldn't have erased it, but all right, and I'm going to label each of these vertices with its degree. The degree of this vertex is 2, right? There's 2 edges incident to this vertex. What about the degree of this vertex B? Well, it has 2 edges incident to it and 1 loop. So we're going to have 2 plus the loop, which counts twice. So 2 plus 2, this has degree 4. Okay, and the idea is like if you really zoom in on this vertex, it looks like there's 4 edges coming out of it. And so that's why we call it degree 4. Here there's 3 edges, so it's degree 3, and this has degree 0. There's no edges out of it. Okay, one last kind of example that we're going to look at today is there's this very famous example in graph theory called the Konigsberg bridge problem. And we're not going to worry about that problem today because we're not ready for it, but we will be ready for it. But I'm going to give you a sense of what the problem said. It said we had this city, Konigsberg, and it had 7 bridges before the war, where some of the bridges were bombed. But we have these regions that look like this. All right, so this top region I'm going to call region B, region A, region C, region D, and then this region here is the river. Okay, and so there were a bunch of bridges connecting these parts of Konigsberg. There was a bridge from A to C, another bridge from A to C, a bridge here, a bridge here, a bridge here, and 2 bridges from A to B. Okay, and then the challenge is which we're not going to solve today. Basically, there's a famous problem where is it possible to start anywhere in Konigsberg and travel across each bridge exactly once? All right, and so that's going to be something we're going to want to solve. But what we're going to do is we're going to identify this map of Konigsberg with a graph. Okay, and so how are we going to do that? One way to do that is we could have these land masses be represented by vertices, and the bridges will be represented by edges. All right, so this map of Konigsberg can be represented with the graph. Here's B, here's A, here's C, here's D. Okay, so those are our 4 land masses, and then an edge will represent that there's a bridge between them. And so we have 2 edges from B to A, 2 from A to C, 1 from C to D, 1 here, and 1 here. All right, so this is a technique that we're going to use throughout this course of taking a map and representing a graph to capture the important details of the map. Okay, well, that's all I have for you today. Let me know in the comments if you have any questions. And yeah, I'll see you in the next one. Take care. Bye-bye.